Hi guys, so here we're going to talk about something called percent errors. This is what we do usually in lab. You'll need your notes, table T, you'll also need table S for this one, and a calculator. So you're going to talk about what percent error is, the different types of errors that happen in lab, how to calculate percent error, and an example. So percent error is pretty much how far away you are from the expected results when you're in lab. So when you're doing an experiment, you get a result, and then you compare that result with what the known values are supposed to be. That is your percent error. And you want a low percent error, so usually less than 10% is good. It also depends on the lab. So something called titrations that we'll do in Unit 4, you want a percent error less than 5% for that one. So there's different types of errors that we have in lab. One's called a systematic error. So this is affecting every single person no matter how many times that they do this experiment. This can be due to imperfections of the equipment. So say for example it's not, like the equipment itself isn't reading correctly. We might have to failure to account for a certain factor, kind of like environmental factors. So if we forgot to account for like temperature or something, if we didn't calibrate it, so for example, if we didn't calibrate our electronic balance, this would be a systematic error. Instrumental drift is pretty much as the lab equipment ages. Not all of it will read the same way each time. So for example, when we have a pH meter, if as time goes on, the older it gets, it might end up not reading as well as it did when it was brand new out of the package. Also, we have lag time. So, for example, if we're heating something up and we take a temperature, we may not have waited long enough in order for that thermometer to pretty much reach equilibrium or be able to read the temperature enough. All right, so you might have gone through it too quickly and didn't read it or didn't let the temperature actually come to the full amount. These are reproducible and are reduced by increasing the number of observations, meaning repeating your experiment. We can also apply a correction factor. For example, some of our thermometers don't read exactly what it's supposed to do, so we can multiply by a certain correction factor for that. Random errors are the errors that we just don't know why it happened. Most of the time it's due to the instrument itself, like the resolution or how precise it is, and this can be reduced by, again, repeating your experiment many times. Personal errors. This is something that can be prevented. This is due to carelessness or poor technique in lab. So you could measure something incorrectly. For example, you can measure a graduated cylinder incorrectly. And use a better technique and also confirm your measurements. So for example, if you need to read what the graduated cylinder is, you read it, have the person next to you read it as well, and then compare what your measurements were. Whenever we're writing a lab report, we can include the other two types of errors, but personal errors we want to avoid because those should have been avoided to begin with in lab. So if you find that your experiment didn't happen the way it was supposed to happen, repeat your experiment, and that has been known to occur as well, so that's okay. Your percent error calculation is found on table T. So its percent error is equal to the measured value minus the accepted value over the accepted value. So the measured value, that's what you have in lab. That's what your lab results were, or the student's lab results or whatever. The accepted value, that's something that I could give you, or you could find it on table S if it was for like density, or from the internet. So this is what be given to you. And that's all over the accepted value. Again, that same value here and here, those two should be the same, and all of it should be multiplied by 100 because it is percent. So you have to multiply by 100. Alright, so an example. You've measured the mass of a sample of aluminum to be 175.5 grams and the volume to be 60.0 centimeters cubed. Determine the density and your percent error. So first we have to do the density. So density, is our unknown. Let me get that in there. Density is unknown. Your mass is 175.5 grams. And your volume is 60 centimeters cubed. So let's plug this in. D is equal to M over V. So it's 175.5 grams over 60.0 centimeters cubed. And for the density itself, we want to make sure that we have that in proper sig figs. So the calculator would have given you 2.925. Hopefully you calculated that out as well. So let's figure out how many sig figs we had. This had 4 sig figs, so the mass had 4 sig figs, the volume had 3, so we'd make sure we round this to 3 sig figs. So 1, 2, 3, draw a line between the 2 and the 5, that 5 makes that 2 go up, so it ends up being 2.93, and then grams per centimeters cubed. Put a box around it. The next thing is we have to figure out is our percent error. Now, whenever we're not essentially finished the calculation yet, because the density, that's the value given, but we're actually going to use the calculator amount, that one, in order to plug into percent error calculation, because we don't want to round in the middle of a calculation. So we did round at the end of density, that's fine, but to find percent error, we want to make sure we keep going. So the experimental density, that's our measured value. Whoopsies. Hold on one second. Alright, now we're back. Okay, so the experimental density, that was our measured value. So we have 2.925 grams per centimeters cubed minus the accepted value. So this time we're going to use table S to help us figure this out because we have aluminum right here, and the density of aluminum, let's find aluminum, is that, 2.70. So 2.70 grams per centimeters cubed. So if we're subtracting, the units are the same, and that's good. And the accepted value, again, 2.70 grams per centimeters cubed. And all of this should be multiplied by 100. So I can't squeeze it into my screen, but hopefully you can for yourself. So it's times 100. So let's plug this into our calculator. Do the top part first. So 2.925 minus 2.70. Press enter. Then divide 2.70. Press enter again, and then multiply that by 100. So you should have a whole bunch of numbers listed for you. Let's figure out how many sig figs. Multiplication and division usually take precedence in the number of sig figs, so when we're dividing, we end up having 3 sig figs at the end. So we should have 8.33, and the unit is percent, hence percent error. So box your final answer and you're good to go. And again, don't forget to make sure that you put that 100 in there. I wasn't able to fit that on my screen, but you will be able to on your paper. So use the formula from table T, find the values from table S or from me, and avoid any personal errors in lab. Have a great day, guys.